One. Number 42 is special. I didn't get number 42. Okay, so I'm a cosmologist, which means if it's closer than 1 billion light years away, I don't care. So I'm talking about planets, which means about 1 in 5 things I say is completely wrong. And I'm not going to tell you which 20% is wrong. You'll have to figure that out. So we've got a great setup in the first half from the theory of planet formation, of how not only do we live on a watery terrestrial planet, but you now know that the theory of how planets form leads you to expect that this phenomenon should not be unique. We should not be surprised if the Earth is not a unique world. And what's special about the Earth, as far as we're concerned in terms of planets, is that it's a living planet, a biological world. So that's sort of the heart of what I want to get to, is what is the observational information on how many planets like ours, roughly like ours, exist. And the first thing I'll point out is that astrobiology is the field, the search for life in the universe. And as we speak, 2017, there is only one planet in the universe that we know of that has biology or life. It's this one. So why are astronomers in general, and astrobiologists in particular, so confident that life exists elsewhere? And it's a set of indirect arguments. It's the fact that the ingredients for life form widely in space, including water. Not a special ingredient, really. It's one of the most abundant molecules in the universe. It's been found on galaxies 12 billion light years away. So water is everywhere. And as you've just seen, you don't need that much water to make a nice watery world with biology. 0.04%. That's all. Not much. Also, we found abundant locations, and that's the number I'm going to put. I'm going to put a number on how many locations are habitable, more or less. You can also look at the history of our planet and decide that life formed, we think, about 3.7, 3.8 billion years ago, a long time ago, and the Earth was pretty inhospitable. If you had been alive 3.8 billion years ago on the Earth, you'd be dead in a couple of minutes because there's no oxygen, it's a pretty nasty place. So life formed under pretty inhospitable circumstances, and we found life in almost every location we looked. Inconceivable places, life that lives beyond the boiling point of water, below its freezing point, that metabolizes toxic metals, that and so on. Lives in pHs from battery acid to drain things. So biology is very sturdy. And so all of these things taken together, before you ever find life elsewhere, lead you to anticipate that it exists. So if you've been paying attention to the news, and there's stories pretty much every week, you'll know that there's a lot of exoplanets being discovered, and more all the time. The first exoplanets were found by this indirect method where the planet causes the star to wobble. You don't see the planet directly. You observe the wobble of the star in its Doppler shift. And the first few hundred planets were found that way, beyond the Earth, beyond the solar system. As you see in that little animation, if the orbit of the planet is in the equatorial plane, you have a second phenomenon that's possible, which is the eclipse. The fact that the planet can cross the face of the star and dim it slightly and periodically every orbit. And that became the second technique, which, in the hands of the Kepler mission, sort of overwhelmed the Doppler method to become the way we found most of the planets that you'll see in the catalog. And the thing that you should recognize is the phenomenal progress in this field. This is a progress from the first few decades of exoplanet discovery. The first found in 1995, and it was a fraction of a Jupiter mass. So these were Jupiter-like planets, gas giants, not habitable, not that interesting for people who care about life and biology. But look at the steady march over time. And remember, this is a logarithmic plot, linear in time, logarithmic, and it's based on pure instrumentation, pure technique. It's not that we got a lot of big telescopes or light gathering. A lot of this work is done with small telescopes. It's profound test diminution of the light from an eclipse.
And you'll see that in just 2 decades, not only ballooned the number of exoplanets, but marched the detection limit down from a Jupiter-like object, which isn't that interesting, who cares if there are Jupiters out there, to an Earth-like object. Whoa, that's pretty interesting. We sort of care if there are Earths out there. And the first Earth-like planets were found just a few years ago. So this is phenomenal progress, and this is the source of all the news stories you read. And of course, the bulk of the planets in the last 5 years, mostly because of one mission, NASA's Kepler, have been found by this eclipse method. Here you'll see like a Jupiter-sized planet crossing the face of a sun-like star. It's a tenth the size of the star. It dims it by the square of that, so 1%. Earth is 10 times smaller, so it's the square of that again, and it's 1/100% dimming of the sun, crossing the sun. Sounds small, actually not hard to detect from space. That's what Kepler was built for. So it's actually pretty routine to detect Earth-like planets by the transit or eclipse method. And the proof is of the pudding is in the eating, and you can see the actually pretty thirsty. I think I need another train in a few minutes, but so you can see the same 20-year history, how the number of planets sort of bumbled along and grew steadily, and then bang, Kepler's launched, and in waves, there was one data release where 1,200 candidate exoplanets were released in one press release. So phenomenal progress in this field, this brand new field of astrophysics. And so now we have of order 5,000 exoplanets, not all fully confirmed, but 90% probable to be real, in catalogs. And in 1994, we had 0. This is a brand new field. But that incredible trawl of exoplanets lets us to start drilling in and asking questions about their habitability, about their properties, about which fraction of them are potentially interesting for biology. So that's what I'm really heading towards here. And here you see the trawl as of just after Kepler's huge release last year. You can see that Kepler is actually able to find almost Mars mass objects, so less than an Earth mass. It's actually measuring size, not mass, so I'll use those loosely and interchangeably. And you can see that this is very recent. So 5 years ago, we knew of 0 Earth-like planets, and there you go. Kepler now has 1,000. You've gone from 0 to 1,000 Earth-like planets in 5 years. Just ridiculous progress. It's kind of shitty if you happen to be a graduate student working in this field, because if you were in this field 10 years ago, you could find a few Earths and write a paper and get sort of semi-famous for a little while. Now you have to find hundreds of Earths, or you have to find the weirdest, most exotic planet. The field is getting crowded, it's busy, it's maturing, of course, and that's great, because that's telling us a lot about the universe we live in. And we've even found individual systems like the TRAPPIST system that was announced not that long ago, less than a year ago, where here compared to the solar system below, you have multiple terrestrial planets. So you have 3 potentially habitable Earth-like planets in one star system. So it's no longer just finding one planet per star. There's a couple of exoplanet systems that have 9 and possibly 11 exoplanets. And since we've booted Pluto out of the solar system, those are exoplanet systems that are richer than the solar system. So it's not just finding a lot of exoplanets around a lot of stars, it's finding a lot of exoplanets per system, and interesting systems of exoplanets, many of which are terrestrial or Earth-like, or potentially Earth-like. So let's put all this together, taking the surveys, what does it say about the fraction of planets of interesting sizes or masses, like Earth, around all stars, any star, including, most importantly, the kind of stars you've been hearing about, the M dwarfs, which are the most abundant stars in the universe and in the galaxy. And you can see here, it's pretty easy, about 1 in 6 stars of any kind has a truly Earth-like planet. And 1 in 4 or 1 in 3 has an Earth or a super-Earth. And a super-Earth which is up to a couple of Earth sizes or Earth masses, those are also potentially habitable because they're rocky planets that can hold an atmosphere that will have water on them. We just don't happen to have a super Earth in the solar system. The solar system turns out to be a slight oddball because the solar system has the Earth, has Venus, which is sort of a clone of the Earth, and Mars, which is low mass and on the edge of habitability. We don't have a super Earth in the solar system, but out there in the larger universe, super Earths are quite common. They're slightly more abundant than Earth-like planets, and they definitely count in the habitability stakes. So, people who are trying to put numbers on this are now homing in not just on the planet's size and its relation to Earth, but also on its orbital period. So now let's look for the sweet spot, that Earth-like position, a true Earth clone. And that's a very restrictive and precise way of looking for an Earth-like planet. It doesn't mean there aren't fully habitable, potentially biological worlds that don't have Earth-like orbits, but let's just be very strict. And the Kepler actually hasn't quite delivered the percentage in that box, the Earth box, if you like, the Earth clone box. But you don't have to, guess, because you can see the percentages in adjacent parts of orbital parameters, and it's going to be a few percent. So there's going to be 3 or 4% true Earth clones, but many of these other adjacent regions are habitable planets. They're Earth-like planets that are habitable. So it's an enormous number because, of course, Kepler is sampling the nearby universe. So we have to get to that. And you can put numbers on habitability. Habitability is a slightly fungible concept because the traditional definition of habitability is a fairly, conventional and understandable definition, which is that a distance of a planet, a terrestrial planet, from a star where water can be liquid on the surface, like the Earth. And of course that does depend on the atmosphere because we have greenhouse warming of about 16, 17 degrees C from our atmosphere relative to what the surface of the Earth would be if it had no atmosphere. So the atmosphere matters when you're calculating habitability. So you need a model and so on. But that's not a very good definition if you're talking just about biology, because as I mentioned, life on Earth exists independent of the photosynthetic food web. It exists in deep rock. It exists under the ocean in total darkness near hydrothermal vents, etc. So life exists out there that's not in Darwin's warm little pond, where life on Earth may have started. Actually, life on Earth probably started in the oceans, in quite hot environments. So it's, again, a very restricted environment in the traditional habitability, and we should, the numbers are going to be larger than that. It's a way of being conservative when you calculate these numbers. And even if you do that conservative method, this is a calculation done from models out of the University of Puerto Rico on habitability, and you can calculate a habitability index. So that's one number between 0 and 1, where 0 is hell, don't go there, you could never live there, not even on a bad Saturday night. And 1 is perfect, the best of all possible worlds. Voltaire's sense of best of all possible worlds. And so you can see that in these numbers, Mars is 0.64. And so Mars is, we think, sort of on the edge of habitability. It could indeed have life under the surface now. It probably had life on the surface in water a few billion years ago. But you can see easily that there are exoplanets out there that are more habitable than Mars and getting on towards the best of all possible worlds. So these are places where you would have to have a reason to think there was no biology. It would have to be unusual for biology not to be there if Earth is an exemplar of biology. Now, what do I mean by Earth clone? Well, I don't mean as the exact clone of the Earth. Earth 2.0, which when we find it out there, it might be an Proxima Centauri system, is not going to be exactly like the Earth. And if I'm going to give you one sort of downer message, I'm going to give you a very upbeat message of how much life there is in the universe. The downer message is, if we fuck up the planet, excuse my French, that's too bad because the nearest of these Earth clones is going to be a couple of 100 trillion miles away. Just to give you a little perspective on that, the farthest humans have ever been from the Earth is the moon, and that cost in 2017 dollars about $80 billion to send 12 middle-aged white guys from Ohio to the moon to stand on the moon. And that's a lot of money, and if you've noticed, we haven't done it since, so it was pretty hard. And the nearest exoplanet is a million or a few million times further. That's a degree of difficulty that is probably beyond us for quite a while. So there is no bailout clause on the Earth. There is no perfect world to go to. And even if we did, it would only be the Bill Gateses and the Mark Zuckerbergs of the world that could afford to go there. And they'd have to be cryonically frozen and hope that the revival technology would work a few centuries later. I'm not going to bet the farm on that technology. So, you know, these Earths are not practically useful for us. They're intellectually illuminating, but they're not useful for us. Nor is Mars. You know, you've probably heard terraforming Mars. Yeah, sure. The minimum plan that NASA has, and NASA has big things on the shelf, the minimum plan for terraforming Mars, making it habitable so we can go there if we use up the Earth like a Kleenex and throw it away because we're messing it up, is roughly 5,000 years and roughly $100 trillion. It's doable. The technologies exist to terraform Mars. It all can be done. It's not rocket science. It is rocket science, but it's not impossible. But it's just ridiculously expensive. So, you know, this is it, people. This is it. This is our planet. You know, there's no astronomy, planetary science. They're not going to save us from ourselves. Just saying. Okay, and everything I've said about Earths and the number I'm about to put on habitable real estate in the Milky Way and then the universe, remember, is a lower bound because I'm talking about the left-hand item there, habitable planets, Earth-like planets, water, habitable, could be biology, why not? There's actually two other categories. There's exomoons. There are a number of moons. There are probably in the end about a dozen moons in the outer solar system that, based on models and expectations, under the surface, usually under a surface of ice and rock, could have liquid water. And Enceladus is the obvious example because it's making these icy geysers. But there's another 8 or 10 moons out there, way out there in the frozen outer solar system that could have biology under the surface. So if you're talking about habitable real estate for microbes, you should include moons of giant planets. And we have found a border of 5,000 exoplanets. We have found 0 exomoons because it's hard. But they're going to be out there, and they're biological real estate too. Another category that's important, and it comes from the simulations that Geis was talking about, is that in the simulations of solar system formation, many things are tossed out of the system early on because it's very chaotic. You saw the eccentricities, the crossing orbits, the migration, all this crazy stuff that goes on. It actually leads to the ejection of planets, including habitable ones with atmospheres and internal heating. And so there are things called nomads out there. And these are perfectly habitable, respectable Earth-like planets that are just floating in free space because they've been tossed out of their solar systems. And we have detected 0 of them because, of course, they have no star illuminating them, no star to make a Doppler wobble, no star to be eclipsed. They're just dark planets out in free space. And in some models, there's almost an equal number of them to exoplanets. So we're talking about a lot of real estate, okay? And if you want a justification for the space program, I want everyone, you know, okay, let's be blunt here. Science is under attack. You know, I don't take my job for granted. I've got tenure, but, you know, the next grant, I don't know if it's going to happen. There's a lot of, you know, there's a lot of shitty stuff happening out there in the world of science and facts and public understanding. But when I want to make the case for science and why it's worth spending money on, I'll just point out this, that for $400 million, you can hire a great director, James Cameron, definitely a great director, and you can make a really cool movie about life on an exomoon, or you can pay for the Kepler spacecraft that found 1,000 Earths. It cost the freaking same amount of money to make the movie or have the mission that actually did the work and the science. I'd say that's a pretty good deal. I mean, we could have both. We can have great, expensive movies and totally bargain missions like Kepler that transform our understanding of our place in the universe. So what is the census? Let's use an analogy, grains of sand. You know, my brain hurts. I'm an astronomer. I'm used to tossing around large numbers. And of course, the truth is, even I don't really know what they mean. I just toss them around, and people, you know, members of the public go, whoa, that's a big number. And I go, yes, that's a big number. Be impressed. So yes, you can be impressed. And I don't understand them either. So let's use grains of sand. The number of truly Earth-like habitable clone planets is if you dip your finger in the wet sand and you have some sand grains. And remember, most of these are in the nearby universe. Kepler really only found most of its planets, the thousands that it's found, are within a few hundred light years, out to a few thousand, but mostly within a few hundred light years. The Milky Way is 100,000 light years across. So we're talking about the backyard, the neighborhood, the hood. So there's 80 Earth-like planets in the hood, and the galaxy, in this analogy, is the sandbox. And so the number of fully, you've got every right to expect biology on these places, is the number of grains of sand in the sandbox, in the Milky Way galaxy. Okay, that's really hard to understand, so we'll use another analogy of a little travelogue. So let's just imagine, we can't do this, because I said the nearest one is 100 trillion miles away, and we've just been to the moon, and that's 1,000,000 times closer. Just imagine we can do remote sensing and send spacecraft to all these Earths and just explore them one by one, sequentially, take pictures, sample whether they have life or not, and we'll just put it into a little travelogue, and you'll see one new exoplanet every few seconds, 6 seconds or so. And most of them won't be inhabited. I mean, some of them will be dead. They're Earth-like planets, but they're not all going to be living. So we just get used to these planets, and we look at them, and we send our spacecraft there, and I get to have a drink. So that's a nice little sampler, a little travelogue, and you just saw a dozen, okay? So if we were able to, we don't have the technology, but if we were able to explore in this way all the Earth-like planets in the galaxy, we'd be very drunk because we'd be here for 10,000 years, okay? So that's an analogy in time of how much freaking real estate there is out there, a lot of it. And that brings us to the Drake equation. Okay, so now I have to take this habitable real estate and play it forward. Let's play it forward into the thing that maybe is more interesting. Most people, you know, don't really care about microbes that much. You know, the pond scum that's on your shower curtain, that's just an annoyance, you know. But most of the universe, the life in the universe is mostly going to be microbial. But we're sort of interested in what goes beyond that. But the numbers are pretty spectacular because the Drake equation was formulated to take the numbers, the real estate, the raw real estate available for life in the universe, and try and play it forward into entities like us, which is getting interesting. And what's interesting in the last decade is that these numbers have been now defined by astronomy. Astronomy can easily count the number of stars in the galaxy, the very high fraction of those that have planets, and now a pretty hard number, order of magnitude, of the fully habitable planets in the Milky Way. It's an enormous number. And so in the Drake equation, it's some fraction of those that actually have life. Some fraction that are habitable will not be inhabited, that will be sterile. Petri dishes where no biological experiment happened. But even if the fraction where something happens is 10%, you're talking about 1 billion biological experiments. Well, that's interesting. And you've got a lot of real estate of time, too. The universe is almost 14 billion years old. So what happens to those biological experiments in 14 billion years? Do some of them develop intelligence or technology? It's happened on the Earth. And you can say it's rare. You can say of the hundreds of millions of species in the history of the Earth, only a handful, elephants, dolphins, perhaps humans, I'm not sure about us, are intelligent. But it's a small number, right? And that doesn't matter because, again, you've got a lot of experiments to work from. And so we don't know how many cosmic pen pals we have in the Milky Way. But the numbers are provocative because they sort of argue that unless the evolution from habitability through life to intelligence and technology is really rare or just goes wrong almost all the time, it's going to be out there. So that's what is now put in front of us. It was all speculation until 1995, total speculation. And even until 5 years ago, until we found Earth-like planets, you're pretty much guessing. Now you've pretty much got to take these numbers seriously. And as a cosmologist, I will point out to you that the Milky Way is just a typical galaxy. And so if you're asking the epistemological question, is there life in the universe, not is there life in our backyard, then here's the number. It's 10 to the power 19, 1 with 19 zeros, fully habitable, biological experiments, if you like, in the universe. And are you going to tell me that they're all dead and nothing happened on any of them? You can tell me that, and I can't prove you wrong, logically, but I don't think so. So, is there life in the universe? Well, I'm pretty damn sure there's life in the universe. Now, it might be very far away. That's part of the issue. But the number of biological worlds in the universe is the number of grains of sand on this arc of beach in Hawaii. So 5 miles and 5 meters deep and 50 meters across. Just to conceptualize the number of sand grains if you can, and each of them is a biological experiment somewhere in the universe. That's pretty wild. And then, as I point out, the real estate of time is as important as the real estate of space. There was enough carbon, I said there was water in the universe at a distance of 12 billion light years. That also means there was water in the universe 12 billion years ago. There was carbon and water and oxygen and all these things 13 billion years ago. So there were fully Earth-cloned planets that got a head start on this planet by 6, 7, 8 billion years. So if biology started on those Earth clones, it could be that much ahead of us. And then your mind just breaks because you can't really imagine what that means. So it's not just that they're out there, but these experiments have been going on longer than the Earth has existed. So here's my trivia question. 5 choices. There's a lot of words, so I'll give you a minute to read the words. The question is, finding Earth-like planets has become routine. What is likely to be the next major advance in this field? This is where's the research headed right now?
Right here. You at the bar. Me? Yeah. Me.
Well, he's right. Nice one. First time. So, and B, it's a little small to read, but B is using spectroscopy to detect microbial life by change in the atmosphere of the planet. So let me talk about the other options briefly because they're interesting too, and they're not absolutely ruled out. This is multiple choice where there's a best answer, but the other ones are not ridiculous. So you've got detecting technological civilizations by receipt of radio signals. That's called SETI, and that's clearly possible, but most people consider unlikely because they've been doing it for 60 years with no success. So it's possible. You've got the idea of taking images of Earth-like planets and actually seeing evidence of civilizations or water or continents. It sounds good, and there have been images made of about 50 of the 5,000 exoplanets, but that is just super hard. Telescopes are just not good enough, and Earth-like planets are just too small to resolve them and see what's going on them. So that just turns out to be really hard for technical reasons. Then you've got the idea of going there with cryogenic methods that I alluded to, and that's possible. I mean, I think the technology to do that, to cryogenically freeze us and maybe revive us, will be there within a few decades. But to get to a reasonable speed is going to take centuries. So that's not going to happen. there's also the idea of sending miniature robotic probes, and I'm going to talk about that in a minute. That is possible. It's called breakthrough starshot. And then there's the answer that is very exciting because there are missions, there are big telescopes like the one we're building in Chile, the Giant Magellan Telescope, 22 meters, biggest telescope in the world, and space missions that are going to try and take the feeble reflected light of an exo-Earth, smear it into a spectrum, and look for the imprint of gases that indicate life. And on Earth, that means oxygen. If the biosphere of the Earth shut down tonight, just say it's a really bad night and the Earth dies at midnight, the whole Earth, everything, all life on Earth dead at midnight, the 1 part in 5 of oxygen that you're breathing in the air would be gone in about 5 or 6 million years, very short, on a geological timescale, because it's sustained entirely by life. It would dissolve in the oceans and oxidize rocks and rust things. So reversing that argument, the oxygen in our atmosphere, 1 part in 5, is a telltale of biology, and it was put there by microbes 2 or 3 billion years ago, not by us. So astronomers are going to use that as the telltale for life elsewhere. And that experiment is on the edge of viability. That'll happen in the next 5 to 7 years. Pay attention, because that will be the news story that says we found life beyond Earth. That's my guess. We said he could always succeed, you never know, but that's my guess as to how we'll find life beyond Earth in your lifetimes and actually quite soon. So the last part of my talk, let me just take what I've done and just go off the deep end. Why not? We're in a bar. I'm on my second beer. We can go a little far here. So, well, there are all these Earths, and there's likely to be all this biology. And you saw the Drake equation. It's like, okay, something's going to be happening on those planets. So what does it imply? And again, some of this may be close by. We know that there's a good bed of Earth-like habitable planets, even in the nearest star system. We've got Proxima Centauri b, which is an Earth-like planet. We don't know if it's truly habitable, but it's close. And so, last year, with big fanfare, these esteemed people, including Stephen Hawking and others, talked about a project to send miniature robotic probes, nanobots, essentially. It's very clever. It uses super high-powered lasers and little solar sails. So the nanobots are maybe a gram or less. The sails are 1 meter. And you're using solar radiation to accelerate the nanobots to 3 or 4 or 5% the speed of light, and then they decelerate, reversing that at the far end. And each of these little nanobots has cameras, remote sensing equipment, and you send lots of them, thousands for redundancy, and they drift down into the atmosphere of your exo-Earth and send you back pictures. And the pictures come back at light speed, which means you've got a 4.5 year delay. But that's the way we see what's on the nearest exo-Earth. Super cool experiment, really cool. And so, and occasionally when you're mired in the mud of science under attack and you couldn't get your last grant, it's amazing and it's refreshing that there are people thinking of these experiments and actually planning them. So Breakthrough Starshot has $100 million seed money from Yuri Milner, Russian entrepreneur. It's not really enough to do the experiment, but it's enough to show if it's viable. And at about 1/10 or 5% of light speed, it'll take you 2 generations, 50 years to get to Proxima Centauri. But they are planning to do the experiment. They're not intimidated by the technological obstacles. So that's really cool. That experiment will probably happen. The other experiments that will happen, of course, are the improvement of SETI. So SETI is vaulting over the uncertainty of whether microbial life becomes technological intelligent like us, and tries to look for the signatures of that life by their deliberate, conscious attempts to communicate. And to do that, it uses 2 methods. It uses radio technology, and radio waves have the advantage of being low energy, so they're energetically cheap to produce, and they travel freely through the universe without obscuration by dust. So radio waves are popular. And the other method, of course, is pulse lasers, because our best lasers actually have enough energy that if you concentrate the highest power laser on the Earth into a picosecond, then in that picosecond it exceeds the sun's energy. And that means that hypothetically, if you're looking for a civilization around a sun-like star, and the sun-like star is sort of blinding you to not see the planet, if that civilization was pulsing lasers at you, you just need to sample the light of that star and you could see the little signal on the top of that civilization pulsing its laser at you. Very clever. So both methods are being used. And the technology is improving rapidly. So SETI people, you know, I'm kind of instant gratification. If I do an experiment at a telescope and it doesn't work after 2 years or 3 years, I pretty much give up. Well, SETI people have been doing their thing for 60 years. Jill Tarter is retired and she started doing it as a grad student. And I was like, whoa, you're made of tough stuff. I could never do it that long. But what they will say, those people who are looking for intelligent signals from civilizations, is that it's just getting interesting. Because our technological capabilities are such that in the logic of this, we can now detect the equivalent of our radio and laser technology on planets around 100 million stars in the Milky Way. Such that if we see nothing after surveying 100 million stars, we can start to say, whoa, you know, the great silence, as it's called in SETI, didn't really mean anything when the sensitivity of the experiments was low, but when the sensitivity of the experiments is high, then it starts to mean there's nobody out there, or they're not using these methods, or both. So SETI is going to keep doing its thing. The other thing we should notice, especially with the Breakthrough Starshot example, is that we're close to having the ability to send nanobots through space at some fraction of light speed. Maybe only a few percent. You don't have to mess with relativity and the energetic cost. And if any civilization can do that, then they could explore or remote sense the galaxy in 10 million years, which is a fraction of the age of the galaxy. And that leads to the question, why should since we're on the edge of that capability, why should we be the first? Maybe someone else has done this. Or why haven't they? Or would we know about it if they had? And so these are provocative questions. And our time in development of technology is very interesting, because the other thing we can say, in addition to being able to create nanobots to travel through space, and perhaps von Neumann machines that can mine asteroids and make replicas of themselves and exponentiate, okay, maybe not that for a while, but the other thing we can say is that computers have progressed to the point where in this graph, it's a little hard to read, but basically this is, I'll just explain it. It's from roboticists, people who combine the robotic and the AI capability of computers. They will say that given Moore's law, and really computers have been advancing this way for a century, not just since semiconductor era 30, 40 years ago. If you ask what is the equivalent life form to the best robotic computational entity we could create in the lab, it's something like a lizard, like a guppy, or a low-grade lizard that could move around an environment and avoid threats and find food or resources or energy. Okay, that sounds about right. But if you look at the extrapolation, we're only a few decades away from creating human-like intelligence, and you've seen hints of it in AI. It's very artificial. I mean, a computer that plays Go is not a computer that can survive in the real world. But you can see where it's headed. And so the question is, if we are about to do this, then why should we be the first to have done this? If we're about to send robotic probes through the galaxy, why should we be the first? There's been so much time for it to happen. And if we're not the first, what does that mean? And this is the Fermi question, so I'm getting to the end of it. The Fermi question was this brilliant dude, Enrico Fermi. He was, by physicists, he was nicknamed the Pope, and he wasn't Catholic. It's because he was considered infallible on issues of physics. And he was sitting jawing with some colleagues at the University of Chicago. Nice story. And they were in the canteen, and they were just talking about all sorts of things. And they were looking at a local paper, and there were two stories on adjacent pages in the local Chicago paper. One was about kids in a Chicago neighborhood that were stealing garbage can lids. And the other on page 3 was about UFO sightings in Chicago. There have been UFO sightings for 60 years. And they sort of saw these two stories, and then they left because they connected them. And they thought, oh, the teenagers are throwing garbage can lids in front of people's windows, making them think they're flying saucers. So they just laughed, and they had a little light moment. And then Fermi was sitting there, and his mind was going, and he just said, where are they? And so what Fermi had done in his head is and remember, this is way before exoplanets were found or anything. This was 1950, for God's sake. He imputed the fact that there are likely to be habitable planets out there, that the ingredients for biology are likely to be widespread, that our technological progression is likely to let us leave the planet. And he said, they should be out there. Where are they? And so this has become the Fermi question. Some people call it a paradox, and I've already had philosophers slap me on the head for using that word because it means something very particular in philosophy. It's a question. Where are they? So, having done the setup of 10 billion habitable worlds in the Milky Way and the Drake equation, and the fact that we're on the imminence of becoming one of these galactic civilizations, let's answer the Fermi question. Where the hell are they? It's not us, but where are the others? And responses to Fermi, well, they vary. They might not exist. We might be freaks. There may be reasons things go wrong. You know, we nearly blew ourselves up in the depths of the Cold War, and we could do it again. We might have pathogens that take us out anyway. We know we're on the edge of viability as a civilization. Let's be honest. So it just may be unstable. So maybe it just goes wrong, and they just don't exist, and we're it. They may be very rare, so we're isolated in time and space. They may be unrecognizable. Now, once you've recognized that they may be more advanced than us, it gets interesting, because why should we even recognize them? Why should they want us to know of their existence? That's some anthropocentric Star Trek type trope, that we're about to join this galactic federation where everyone has weapons, but they're all more or less equal, and you win some and lose some. You know, that's ridiculous. That's not likely to be the real universe we live in. So they could be inscrutable, and they could not care about us. I mean, if we went to the first 100 habitable planets with our tricorders and looked on life, and we said, oh, that one's dead, and then we found some lichen on a rock or whatever, we just said, oh, lichen on a rock, you know. Well, if they're as advanced to us as we are to lichen, then they won't care about us. Why should they care about us? And then there's a sort of theistic and slightly creepy implication, which is that if they had sufficiently advanced capabilities, they definitely could have created us. It's not that hard. So that's got to be in there too. So let me just finish, getting to the end here, with analogies, which is why it's so hard to play this forward in your head, because we're here at a snapshot in time and space. You know, we have the cable and TV shows that we like, we have the social media that we like, and that is so ridiculously ephemeral. It won't matter a damn in 10 years and 100 years and 1,000 years. It'll barely be a relic of our culture. Who will know? Who will care? All the stuff we care about so much every day. So let's just analogize technology. First human technologies of hunting. You know, arrowheads. An arrowhead is to an iPhone as an iPhone is to what? Could you do that analogy in your head? I can't. What about the evolution one, which is more relevant because of that real estate of time? A microbe is to us, super sophisticated, savvy, social media, wireless internet, as we are to what? 3 billion years more advanced. I can't imagine that, and I challenge you to imagine that too. We still have this very exalted opinion of ourselves. You know, we may resist it, but there's a little piece of us that kind of thinks our shit doesn't stink. You know, we go around the planet like that's the case. The aliens might have a slightly different view, you know, and we just might not be as wonderful to them, and we just might be a tool or something useful or utilitarian. Another hypothesis is that they're among us. Johnny von Neumann, there was this spate of super intelligent, smart Hungarian physicists, and von Neumann founded the field of computer science, another Hungarian. And when von Neumann was talking to Fermi about all this alien stuff, von Neumann said, they're the Hungarians, you know, the aliens are here and they're the Hungarians. So maybe they're already among us. And that's a reasonable hypothesis that needs to be refuted with evidence. But I think what we also see, regardless of your inclinations, and I'm not religious by any stretch, we have mapped into this unknown other out there that we think now by inference, by scientific inference, should exist. We have mapped all our hopes, our fears, our longings, our dreams, our nightmares of salvation and redemption and damnation from the situation that we find ourselves in. And until we actually get the answer through science, through exploration, we're just going to have to stew in that. And I'll leave you with that. Thank you.